Recording in
Hello,
progress.
everybody. Welcome to our next major topic in Chem 220, which is this idea of chemical equilibrium. So let's think a little bit about where we've been so far in Chem 220, and I think that'll give us some really good context as to where we're headed. So thus far in Chem 220, we've really been focusing on thinking about what's going on in solution. So what's the solute, what's the solvent, what kind of intermolecular forces are being enacted between them, how do we describe a solution according to its concentration, things of that nature. Colligative properties, right? Physical properties of substances, solutions. Why? Why have we been talking so much about properties of solutions and in general just trying to like situate ourselves in the beaker when we think about what's going on in a chemical process? Well, the main reason I start us with colligative properties of solutions and general solution properties overall is that when we move to this next topic of chemical equilibrium, we are going to be zooming in very, very closely to look at chemical reactions that are happening oftentimes in aqueous medium, right? We often look at aqueous reactions in Chem 210, 220. So it's useful for us to have this kind of like priming of a molecular view of what's going on in solution, because that will help us understand the complexity that we're adding to our understanding of how a chemical reaction happens in solution. So let's talk about that complexity. And we have a name for it. It's this notion of chemical equilibrium. So let's talk about it. Chemical equilibrium. In order to talk about chemical equilibrium, we should probably have a sense of what equilibrium itself is. So, as stated here in the title, I have said that equilibrium has seemingly static processes that are actually existing as a dynamic process. So, in a state of equilibrium, so systems in a state of equilibrium are systems where a constant change is occurring, but net overall, the net change is zero. So we have seen some examples of states in equilibrium or systems in equilibrium in Chem 220 so far. So for example, we've looked at phase equilibria. So we've looked at vapor pressure in our conversation about vapor pressure lowering. So if I've got a system that is a liquid in a closed container, then the molecules of that liquid substance will spontaneously, will naturally escape up into the vapor phase or vaporize. So that doesn't mean they're boiling, but they vaporize. So I would expect to find some of those particles in the vapor phase. And when you and I look at this little diagram that we've drawn a couple of times, right, it looks like we have a static or like a non-changing thing that's happening in the beaker. It looks like we've just got molecules that exist up here in the gaseous phase, and then molecules that exist on their own here in the liquid phase. And like that's kind of it, right? The vapor pressure that we could measure from what's going on in the headspace above the liquid is the result of like liquid molecules vaporizing, and then they're like stuck in the vapor phase. However, we know that this is not an accurate portrayal of what's happening when we measure the vapor pressure of solution. So, when looking at a system that is establishing a vapor pressure, we have discussed how there must be some kind of constant exchange which I've drawn with these kind of double arrows here. Between particles that exist in the liquid phase and in the gas phase. So constant exchange between liquid and gas phases. So I've done this before, but let's show it again, just because it's good to see. So if I'm thinking about how these molecules are moving around, twirling, swirling, right, in their mid-level kinetic energy liquid state, if one happens to encounter this boundary here and has sufficient enough energy, it will spontaneously vaporize and then go up into the gas phase where it has a bunch of kinetic energy, exerts a bunch of collisions, right? That's what gives rise to this vapor pressure. But then if it finds this boundary layer again, it will go back down into the liquid phase. And this process repeats over and over and over again, going from the vapor phase down into the liquid phase, into the vapor phase, and down into the liquid phase. So despite us looking at, let's say, like a closed water bottle that has, some condensation that's formed on the top, that looks like, one change has happened and then that's it, that's fixed, right? Like it doesn't look, we don't see an active change in our water bottle. But there has to be some kind of active exchange, constant change, this dynamicism that's happening in order for our particles to continually go from being in the vapor phase to being in the liquid phase. So that's what I mean when I say seemingly static. It looks like there's no change when in reality, there is a constant exchange. Now, the thing about states in equilibrium is if a system is in a state of dynamic, meaning constant perpetual change, equilibrium, we observe no net change in the system, meaning like, why is it that that water bottle would appear seemingly static, even though we know there's a constant phase interaction, or excuse me, phase equilibrium that's set up inside that water bottle? And that is because if a system is in that state of equilibrium, we observe no net change in the system because at equilibrium, the rate of one process, or I should say one half of the process, is equal to the rate of the other half. So we are going to be considering things like chemical reactions with this lens of dynamic equilibrium being established in that reaction. So we're going to look at like this whole system, like a holistic perspective of what's going on in a chemical reaction, just like we look at a holistic system for vapor pressure. We consider everything that's going on inside of that beaker. And we're going to recognize that the only way that we can observe this equilibrium state and it looks to us like nothing's really changing, that's because whatever's happening with one part of the process, how quickly that's happening, so in this case, this would be the vaporization rate, would have to be equal to the rate of the other part of the process. So here in our example, we would say the rate of vaporization is equal to the rate of condensation. So for every one molecule that manages to escape into the vapor phase, there's also one returning to the liquid phase at the same rate. So this is why we observe no net change. Now, what does that have to do with like an actual chemical system being like, instead of looking at a phase equilibrium, what if we look at a chemical reaction? So in Chem 210 or Gen Chem 1, we made a major assumption about chemical reactions when we did all of our stoichiometry, when we did our titrations, right? And that main big fat assumption that we made is one that's actually not really true. It's kind of like hand waving the truth away. So in Chem 210, we assumed that all reactions proceed in one, and I'm going to put this in quotes, direction. And this implied that this was some kind of like static change from initial to final. So for example, if we were to look at the reaction of X going to Y in Chem 210 or in Gen Chem 1, the assumption that the reactions proceed in one direction, resulting in just some like net initial final change, was indicated by the fact that we would draw a single-headed arrow, right? We would go from our starting state, our initial, our reaction, or reactants, excuse me, to our final state, the products. And once X had been converted or reacted to create Y, that was it. Reaction done, reaction over. Like I said, this is a actual this is a pretty big assumption to make. In fact, the majority, if not every single chemical reaction, and processes exist in some kind of state of equilibrium. So they exist in a constant state of change, which we would indicate using different notation. So for a reaction in equilibrium, instead of saying X just goes to Y, we would say that the overall chemical reaction of X reacting to Y has a little bit more nuance. This is really a chemical system where we've got not just X going to Y, and that's it, end of story, but rather we have this simultaneous process where X creates Y, and Y also reverts back and recreates X. So we use this double arrow notation to indicate that we are, in fact, a system that is in equilibrium. So going back to this idea of like what equilibrium means in a general sense, let's apply that here for a chemical reaction. So we would say that the rate of consumption of X has to be equal to the rate of consumption of Y when we reach equilibrium. So if X is being consumed, that's creating Y. And if Y is being consumed, that is creating X. So if we think about like the consumption of a reactant, we would call this the forward reaction, even though it's not like its own discrete reaction, the whole exchange process is the reaction. And then the consumption of products This would be called the reverse reaction or the reverse half of this reaction. And again, these are only conditions that are set up once we are at equilibrium. So let's look at this little graph that I've got over here, which really shows how the concentration of reactant and product can change over time until we achieve equilibrium. So we're looking at reaction time. So here we've got T equals 0, which is like the time right before the reaction begins. So we have some quantity of reactant here. So this is amount of reactant, let's call it X initial. And then down here, we have some amount of product Y initial, and notice this is equal to 0 because the reaction has not yet begun. So as the reaction proceeds, we see that X is consumed and the rate of consumption is pretty steep, right? Like this line I can draw a tangent here is a pretty steep one. And the rate of production of product also pretty steeply increases. And once these two rates equal one another, meaning notice the slope of this line here and the slope of this line here are the same. So these rates are constant. So constant forward rate, constant reverse rate. We have officially achieved our state of being in equilibrium. So X is consumed, Y is made, and then we have this constant back and forth at the state of equilibrium. So this reaction time here, that's indicated by this little like dashed line, this would be the time at which our rates are equivalent and thus equilibrium is established. So let's put that on the board. So this is the T at which equilibrium is established. So let's look at an example of like a little model of what's happening in chemical equilibrium. So let's see here. That's not the slide I want. So we are going to consider a modeled reaction. And just so that you have some context about what you're about to see, we are going to be looking at a reaction that involves like this reactant here reacting with this reactant here. Like this is the shapes of these little made up molecules that we're going to be looking at. So I'm going to put a little demonstration up here on the board. And this is the reaction we're looking at that is going to be creating in equilibrium the combination of these products. So it would look something like this. But combo. So let's take a look. Okay, so here is a GIF that shows this reaction between reactant molecules. So the two molecules here, they collide and form product. So if we're looking at the top of the beaker, reactant molecules come together, form products. But then if we look at the bottom of the beaker, we'll notice that the combined product then unforms itself and goes back to initial reactants. And we are in a state of chemical equilibrium when the rate of reactants coming together to form product and the products dissociating backward to reform reactant are equal to one another. So notice this is a one-to-one exchange. One product formed goes back to being one state of being in the reactant state, right? So products being made, going down toward the bottom. So products being made, and now the reactants moving up top have been unmade. So the product has been unmade. So this would be the forward going down here toward the bottom left and the reverse moving up toward the right. So the rates are equal. Okay. Let's talk about some things that equilibrium is not. So these are some kind of common misconceptions about a state or a reaction at equilibrium. The first is that equilibrium is a state that's obtained when the reaction stops. So these are misconceptions. These are things that are an incorrect assumption about what chemical equilibrium is. So the first is equilibrium is obtained when the reaction stops. The correct idea to think about here is, again, we're talking about a dynamic process. So it's not that the reaction ever like fully concretely stops. We don't have reactant going to product, and then that's all she wrote, right? We've got reactant going to product going to reactant, vice versa. Constant equivalent exchange between this chemical system. So the correction to this misconception, which we'll put here in green, is that equilibrium is a constant state of change between what we're going to call the forward and the reverse parts of the reaction. So there's never any static quality about equilibrium, ever constant change. The next misconception that people tend to find themselves like thinking about when they are thinking about equilibrium is that at equilibrium, the concentrations of reactant and product are equal. So what about this is incorrect? Like, why is this not a correct way of thinking about what's happening at equilibrium? So at equilibrium, concentrations are equal. We know that at equilibrium, the rates of the forward and reverse aspects of our chemical system are constant and equal. So that means that I can exist in a state of equilibrium and I can have more product than I do reactant. The rate of the exchange between those two like sides of this system is constant, But that doesn't necessarily mean that I have to have the same amount of reactant as I do product. So it's not that at equilibrium our concentrations are equal, it's that our rates are equivalent. So I can have kind of like a skew in my equilibrium. We talk about like how your equilibrium favors. So we'll get into that in a moment. And then I think the last misconception is more of a technical one. And it's one that's like kind of the product of lazy language, I think. So the third common misconception people have when they think about equilibrium is that their chemical reaction is two like separate, discrete processes that are exchanging. Now I can see how if you're coming from Chem 210 and like you're just being introduced to the idea of equilibrium, especially since we're using this arrow notation, right, to show the forward and reverse aspects of our chemical reaction. Like I can see how that would make it easier for you to think that I've got like the forward reaction and the reverse reaction as being like two different things that are happening. It is better, I think, for us to correct this misconception by giving ourselves more clear language where we recognize that the chemical reaction in a state of equilibrium is a system in equilibrium. So instead of splitting it into these like two half parts, we have to think of a chemical reaction as being a constant exchange between reactant and product. So again, this goes to this idea of like, remember, there's no staticism in a state of equilibrium. It's a constant change. So now when you're thinking about a chemical reaction, it's no longer just like reactant goes to product, or even if you're thinking about equilibrium, reactant goes to product, and so too product goes to reactant. It is the chemical reaction itself is constantly in exchange. That's what it means to be in equilibrium. So we are thinking about this system as like a holistic whole system instead of just like, here's the one that points toward my reactant and here's the one that points toward my product. That's not something that we want to like get into the habit of thinking of when conceptualizing what's going on at equilibrium. So this is our introduction to like what conceptually equilibrium is. We, of course, are going to get into the mathematics of how we can quantify its state at equilibrium, a state at equilibrium, excuse me. But first, we are going to move on to what we had discussed in lab yesterday, which was what happens to a system that exists in equilibrium when you try to disturb it or disrupt it. So in our next video, we will talk about disruptions to equilibrium and kind of like the general rule of thumb that we could use to predict what might happen that we call Le Chatelier's principle.